So good evening, everyone. So today we want to look at linear regression. As a form of introduction, the term regression is a historical anomaly. It was coined by Francis Galton in the 19th century to describe a biological phenomenon. The phenomenon was that the height of descendants of tall ancestors tend to regress down towards a normal average, a phenomenon also known as regression toward the mean. It simply means that the average value of y is a function of s. That is changing with s, changes with s. The word regression sounds like go back in some ways, go back, regress, go back. The term has appeared in early writings since late 13, that's 14th century, late 13th. And it is derived from the Latin word regressus, which means to return, mean a return. It is used in different fields with different meanings, but in any case, it is always referred to as the action of regressing, going back or returning. In philosophy, regression is used to indicate the inverse logical procedure with respect to that of the normal apodictic, that is demonstrable or indisputable truth, in which we proceed from the general to the particular. Whereas in reality, in regression, we go back from, that is from particular to general, effect to cause, condition to condition, condition to condition. Can you see now? You see effect to cause. That is, for example, now, you want to know what are the causes of diabetes, what are the risk factors for diabetes. So you start with who are those who are diabetic, or what is the blood sugar. See, this is blood sugar. What are the cause now? Effect is the blood sugar. What you think are the determinant or causes of the high blood sugar, diabetic, or the causes, either blood sugar or diabetic, is the effect rather, blood sugar or diabetes. The causes, whether obesity, many risk factors, family history, think of dietary factors, sedentary lifestyle, many things you may think may be the risk factor for diabetics. Those are the causes. But here, you identify that some people, they are diabetic, some people are not diabetic. You want to know, okay, what are those factors that are common among the diabetic that are not common? That are common, that are not common. What are those factors that are common among the diabetics? So you can see now the effect is the diabetes you are looking. So in regression, we said that it's you to find relationship to predict an outcome from some exposure variable. Condition to the condition. The diabetes is the condition. The condition are the things that are causing the diabetes. So let's give some historical prelude. Well, the one I've been giving as the part of it anyway. In statistics, the term regression has ancient origin and very special meaning. The man who coined the term was a certain Francis Galton, was a genetist. The man, in 1889, he published an article in which he demonstrated how every characteristic of an individual is inherited because they are their offspring, but on an average to a lesser degree. That is, some inheritance, some characteristics are inherited by the offspring, but to certain lesser degrees. For example, children with tall parents are also tall, but on the average, their height will be comparatively less than that of their parents. The same thing, children with short parents will be short, but their average height will be higher than that of their parents. This phenomenon, also graphically described, is called regression. Since then, this term has lived on to define statistical techniques that analyze the relationship between two or more variables. So in Gattin's world, this corresponded to the concept of regression towards mediocrity, hence the name of the statistical analysis technique. This is Gattin. In late 80s, Francis Gattin, influenced by his cousin Charles Darwin, begins nature-nurture debate. Charles Darwin, one the proponent of evolution theory, was a cousin to Francis Galton. So it was Charles Darwin that influenced this Francis Galton. In the early 90s, Gregor Mendel genetic work with peace realized as important. In 1920, quantitative genetics developed. 1950, DNA discovered by Watson and Crick. Early 20s, human genome sequence. Now, why do we have all these historical context? I think we'll be able to link events, the way human reason. You know, I told you before that in some of our lecture, that the people that develop is biologists that develop statistics over the year. The biology that contributed most to statistics, followed by social science. Someone like what's the name? This one was a genetics. But some of them they go into other things, geography. I mean, he wrote a lot of things. By that time, he didn't stand in one field. They were writing genetics, write about geography, you know. He was a genetic. Fisher, who developed statistical table, was a genetic. Spearman, that first described chi-square, standard deviation, correlation coefficient, many things. Pearson correlation. And Fisher is that test. ANOVA, Fisher statistic, F statistic. All the Fisher was a genetist. Spearman was a genetist. Can you see? Many of those people, early people that developed statistics as biology, they were genetics as some modern biologists. You will get to know that even Pearson was a student to Francis Galton. Pearson. Can you see? Galton was influenced by Charles Darwin. But Pearson was a student to Galton. So the Galton universal regression law was confirmed by Carl Pearson, who was a student. He collected more than 1,000 heights of members of family group. He found that the average height of the children from a group of short parents was greater than the average height of their father's group. Also, average height of the children from a group of tall fathers was lower than the average height of a group of taller father. Group of tall father was lower than the average height of their parent group. That is, the height of the tall and short children were regressing towards the average height of all people. So If parents are tall, the children will be tall, but not as tall as their parents because they want to be going towards the average in the population. If parents are short, the children will be short, but not as short as their parents because they are trying to go back to the normal in the population. A way, so the statistical techniques now we are talking about is a way of predicting an outcome variable from one predictor variable, that's simple regression, or from several predictor variables, that's multiple regression. So when you predict an outcome, like we say blood sugar now, from one maybe from blood pressure. See, if I know somebody's blood pressure, you know blood sugar. I'm just giving an example. Or BMI, let's say BMI. You know, if it's just one variable that you are using as a factor, that is simple regression. But when you are having more than one, maybe not only that, sex also, apart from the BMI, then maybe other comorbidity, maybe hypertension, many other factors. That is when you want to predict a particular outcome from several factors at the same time. That is called multiple regression. So you can see now, if it is simple regression, the outcome variable is one. The exposure variable is one. That's simple regression. If it is multiple regression, the outcome variable is one, but the exposure variable are many. So as you are going to see now, we talk about linear. This we want to discuss linear regression because most of these statistical tools start with quantitative before they now adapt them to qualitative. So the linear regression was described first before issue of logistic regression. So the difference is the variable you are predicting. If you are predicting quantitative variable, that is linear regression. But if you are predicting categorical variable, that is logistic regression. Irrespective of which type of variable is serving as the exposure, the most important thing is the type of variable that the outcome is. When the outcome is quantitative variable, it's linear regression. When it is categorical variable, it's logistic regression. Any of them can be simple linear regression, multiple logistic linear regression, or simple logistic regression, or multiple logistic regression. We can predict any data using the following general equation. So look at the crude way of just, okay, no statistics you want to see because the essence of statistics is to mirror life situation in an equation or in a graph or on a table. Those are the three ways of modeling life situation, either in an equation or in a graph or on a table. So let's say equation now, the outcome variable is equal to the model and error. So there must be a model that predict that predict that outcome. That model was built from the exposure. I actually give an example that is funny, but it's just for you to make it easier. You know, when people want to, maybe pastor, they want to build new church, cathedral, or whatever, new site or whatever they call it, they go and build the model where they will draw the something, car park, everything. See, they say is a 50,000 capacity auditorium, church auditorium. By the time they do it with everything, all the graphics, they play it. By the time they play it, that's a model. When they play now, by the time they play, people begin to bring money. No, it's they're using to predict. So the what do I call it? The church has not come, but they have built a model. That model, something that represents all those things that will be there. Car park will be there, the auditorium will be there, a children's church will be there, different things will be in that. They will put different things. Those are the things that we make up to to form the church. I will determine the church, the auditorium. They put it as a model. And by the time But it's model from error because by the time they finish building the house, you discover that if you go and put all those pictures, all those things they were showing, and the ratio is not the same, I'll be subdivision. You will not get it exactly. The model will not completely predict what the church will be. So the difference is the error. I just use that one as a social example. Now, in understanding this prediction, because it's about regression now, it's about predicting an exposure from hardcore. Of course, for you to understand, it's better we start with simple linear regression. That is, how do we even predict one variable from only one first? When you understand, you'll be able to know how to accommodate 2, 3, 4, 5. So now, since we say either equation or graph, the simplest, okay, they say some people are in waiting room more. Okay. Maybe should I appoint somebody as, or can I appoint somebody as co, so that can be helping me to, I forgot. So the simplest description of relationship between two continuous variables is a straight line. That is, no, we are talking about linear regression. And the best way to describe it to say, okay, of course, the outcome is continuous. To make it simple, let's say the exposure is continuous variable also. The simplest way to represent in both, to model it in both equation and graph is equation of a straight line. Because what the meaning of equation of a called linear regression, the meaning of equation of a straight line is this. If the straight line is representing two variables, like for weight, the age of a child and the weight of a child. If it's a straight line relationship, so if the age increases by 1, the weight will increase by a certain number. If the age increases by another 1, the weight will increase by the same amount. For each value of the exposure, there's a constant value of the hardcore. That's the meaning of the relationship. It's a straight line relationship, as opposed to other type of relation like quadratic, polynomial, curvilinear. But this one, so now the simplest description equation of a straight line. And this one was borrowed from mathematics. The shape and position of a straight line is defined by two things. In geometry, the shape and position of a straight line is defined by two things: intercept and slope. Where the intercept is where the line crosses y. Look at that equation. Remember this equation of a straight line in mathematics. We say y is equal to mx plus c. Y is the outcome variable we are predicting. X is the exposure. M is the slope, and C is the intercept. C is where the graph crosses the y-axis. The intercept, that's y intercept. Just call it actually y intercept because there's a place also where the graph can cross x-axis. It's x intercept. But that C here is not x, it's y intercept, where the graph cross y-axis. And it's the same thing as the value of y when x is 0. If you remember, the way it crosses, if you trace it down, the x, which is the horizontal one, will be 0 at that point where the graph crosses y. So the value of y when x is 0. So later you get to conceptualize it, that if you are looking at the relation between x and y, and x is the exposure and y is the outcome, and you see have a value of y when the exposure is 0, what does it tell you? It means that wait, it's not only this exposure we are considering that determine X. Other things may determine X. It's only we are considering the exposure we call X. But there will be a value for Y, even when X does not exist. That shows that there are some other factors that determine X in Y, rather. That's a clue. Now, the slope is the gradient. That is how slopy, how slanty, let me use it. How slanty is the graph, is the line. If it is horizontal, it's not slanty. That shows the slope is 0. So as it's tilted, if it's almost flat but tilted, that shows the slope is small. But it's almost vertical and it's tilted, that is very slopy. Slope is high. And to be sincere with you, how do you measure that slope? Whether it's really high, steepy, or not so slopy, is by the value of change in Y over change in X. That is, if you look at that graph now, you see, if you draw 2 points on a graph, on the line, dot, and now draw a vertical line and draw horizontal line at the mid. So now, the change, that vertical line you draw, is the change in Y. The corresponding change in the X is the horizontal. So change in Y per unit, and Y is the outcome. Change in Y per unit, change in X is the slope. That is, if the X change by social amount, what would be the change in Y? If we X change by 1, what would be the change in Y? Change in Y over change in X, a unit change in X. If it's sloping now, you see that that change in Y per unit change will be higher. But if it is not so sloping, almost flat, it will be small. Compare with, can you see the distance? So now, that's just to give you a graphical. So you can see this is equation of a straight line. Intercept is the value of Y when X is 0. Slope is the amount Y increases for each unit increase in X. So let's quickly rattle this slope of it, type of slope generally. Can you see? Put 4 here. Where can you see the one move from? If you move from right to the left to right, upward, slant upward, that's positive slope. Line rises from left to right, down up like that. But if you move from left to right, downward, that's the second one, negative slope. That is, line forms from left to right, that's negative. Slope is 0 when it is horizontal. Slope is vertical when it's not defined. It's not defined. That is, you don't talk about slope here. There's nothing slopey here. It's not defined. Now, let's talk about the intercept. The intercept, where both of them, both slope and intercept, how they relate. You see, what slope and intercept represent. Slope can be here now. We already say it can be, because slope is looking at the shape of the graph in this geometric space, whether it's rising from upward from left to right or downward from left to right. That's the shape. The intercept is the position in geometric, that is location in the geometric space. It can be positive or negative. Just like the way slope can be positive or negative, intercept can be positive or negative. Look at the three scenarios. A line with a positive slope and a positive intercept. Can you see? The slope from left to right upward. Then the intercept. Can you see where the graph cross wires is on the positive? You know when you draw line Y and S, the one that's above up like this for Y is the positive line. The low down horizontal line for Y is the negative For x-axis, anything on to the right of that y vertical axis is positive. Anything to the left is negative. So in that context, you will see that for this first one, slope is positive and the intercept is positive. If you move to the second one on the right side up, a line with a positive slope and a negative intercept, you see that it's still positive slope, but where the line cross y as it is on the negative side of y, which is down below the horizontal line. So that's negative. Because that point when the horizontal and vertical line cross is 0. So when you are labeling, if you are labeling now, from that place to the right side is positive, to the left side is negative. If you are labeling up, or that place up is positive, down is negative. So the slope is positive in this second one, and the intercept is negative. The third one, the slope is negative. You can see slope from left to right downward, but intercept is positive because can you see where it is, where it crosses y. The last one, the slope is negative still, but the intercept is negative also. So can you see now? So those are the 3 or 4 combinations. Combination of the slope. Since we have 2 types of slope, 2 types of intercept, y-intercept, either positive or negative for each of them. So when you combine both of them together, it gives you 4 different options. So let's look at the equation, graphical representation of equation similar to the equation of a straight line. So in mathematics now, it just say y is equal to mx plus c. But in statistics, in regression, it's the same logic. You now say y is equal to bx plus a, or you say a plus. Here they like writing in a first, that intercept first. A plus b, or alpha plus beta x. It's the same slope. Can you see? B is the slope, which is called regression coefficient. B slope is the regression coefficient. It just means that change in y per unit change in x. That is, change in y over unit change in x. That is the regression coefficient. A is a constant, is the y dependent variable when x independent variable is 0. That is the value of y when x is 0. That is, when x is not contributing anything, y still have value. So in the relationship between x and y, when x is not doing anything, y still have value. It's just like if you are a friend, or maybe you have a relationship with somebody, whatever the relationship. When that person that is determining something in your life is responsible for your education, the one responsible, that is the relationship. But if it's not there at all for your education, does that mean that you will not be educated? May not necessarily mean. So that is what A means, constant. The value of y when x is not there is 0. If value of y is equal to a plus bs, that is, it's the same thing. That bs, b in statistics, is like the m in the mathematics. Both of them are slope of the straight line. A in statistics is like the c in mathematics. That is the intercept, y-intercept. So y, when in mathematics, y is equal to mx plus c. It's the same thing as y is equal to bx plus a, or a plus bx. This is the regression equation. Y is equal to a plus b. So if you are dealing with only one, so in writing it in a technical way, you say y, instead of putting that b and e, you say b0, that is that regression coefficient 0, that is when there's no x there. Because look at it, this b1 x1, can you see me that the x, the regression coefficient with x, but the one without x, our value of x0, we call it b0 instead of calling it a. So this first one now is simple linear regression equation. The second one is multiple. When you have many of the x, you have many of the exposure. That's the way it is written. So in another way, in more modern line, technical way. So the way you do it is that if by the time you plot the graph or you find all the value of, you can calculate the, how do you come about predicting it with and. If you calculate the mean of y, you want to calculate the mean of y, you can mean of x, mean of y, be able to know, calculate the slope and the intercept. When you calculate the slope and intercept, that's what you now use to predict f for every value of x to predict y. I wouldn't know the time we have spent. This is the regression model. Maybe I don't know if I should start the discussion on the regression, because we need to discuss how do you actually in real life do this prediction. You will see in the real life, you just see straight line. When that straight line is not actually all the data you use to predict the straight line will not actually fall on that line. So if you collect data now, you plot x and y, x on the y-axis corresponding. For example, now we are talking of a particular person. You're talking about maybe their salt intake, amount of daily salt intake, and their blood pressure. So salt intake will be the x, blood pressure will be the y. So where you put y-axis, the blood pressure on the vertical axis, y-axis, the other one horizontal axis. So all those dots are for each person. So on the x-axis, what is the value of salt intake? On the y-axis, what is the value of blood pressure of that person? Where the meet down. By the time you do, you're going to have something like scatter diagram like this. That all of them may not be on the same. They may be scattered. So what if you are to not give you a biro and a pencil or ruler? Please help us draw the line. Different people will probably draw different things. Different people will draw different things because there's subjectivity. But if we are to know what is the best line to draw, the best line will be a line that passes through. And if we try to now look at the average distance of each dot from that line, of course, if you are to do the average distance, if you want to do it, you cannot do it directly, because if you know what you do is some people, some will be above the line, some will be below the line. So the difference between them, those ones that are above the line mean that they are more than what the line predicted. The ones that are below the line are less. So the one below are negative, the other are positive. If you try to add them together, it gives you 0. So that's the logic behind squaring. When you square, So when you square it now, it change all the value to positive. So if you draw a line and you try to the distance between the line and each value, you try to square it and add it together. You know, when you square it, the negative will become positive, everything will become positive. If everybody, maybe about 5 of us draw the line, different line, I will do that. The one that has better line or the best line among us will be the person that when we square all the distance, the difference between the line and those dots, the distance from each dot and the line, when we square it, the one that gives us the smallest value will be the one that is closer to almost all of them averagely. That is what that best line is called line of best fit. That is the best line you can draw for that regression. The best regression line you can draw. Line of best fit. And the method to get is what I've just said now. By squaring the distance between each of the the distance between the line and each dot. When you square it and add it together, the one that gives you the smelling. So that's why I say the line of best fit is best gotten by using the least least square, what do I call it? Line of best is gotten by using the method of least square, the least square. That is the least the square. That is if you do the square of the difference, the deviation from the line, the one that gives you the least square, line of the least square. So now the least square method is the best. That is when you square each of the distance, it gives you the one that gave you the smallest. That is the least square method. Now, just like what I say, you can use hand, but mathematics, computer has made it easy for us to use computer. It will draw the line for us and give us the best line, give you a line of best fit through the least square method. Least square method, yes. Least square method is the one that is best for that line of best fit or method of least square. Now, hold on.
We can't hear you, sir. Maybe is it just me? Can you hear him?
He said we should hold on.
Can't hear him.
He said we should hold on.
Sorry, I'm back. The only person at home, so nothing. Yeah. You see, now, when the computer does it for us, let's say we have drawn the line now. The next thing is, how best, if the line is drawn, how do you evaluate that this line is the best, this line fits the data very well? How do you do the evaluation? So, yes, that's what I want to, instead of, we treat this is just an example. How do you do that? There are two methods of assessing the goodness of fit for the regression line. That is, when you draw this data, does it fit this model? Does it fit the data very well? Two methods, R square and F ratio. You calculate the R square and F ratio. You remember when you say R square, though they use capital R, but the R per se, where it got the name from, is that Pearson correlation coefficient. If the two variables you are dealing with, you are trying to fit maybe blood pressure on salt intake, amount of salt, daily salt intake, there will be correlation between them. If you square that correlation, it's the same thing as this R square. You're going to see. It's easily proven or best proven if we have data, we use data in real life. So the second one is the F ratio. Remember, we talked about ANOVA. I told you that ANOVA and regression is the same thing. You remember in our F ratio, where we say the variance between divided by the variance within, which is F ratio. It's the same thing here in a different way. So the R square is the proportion of improvement due to the model. I will explain it. So you see this equation now, see R is going to look something. But graphically, if you want to explain it, this is the best way for people to conceptualize. Apart from running the data together so that you see in real life, this is a graphical way. So as I explain it now, I will try to relate this regression with ANOVA or to ANOVA. To be sincere with you, the crudest model is the mean. I think I made mention of it before. If you are to predict a particular, okay, I want to predict blood pressure. The crudest model is the mean blood pressure. The reason why you know that if you have 400 people, you measure their systolic blood pressure. These are the value. You now calculate the average. You now see the average 110 or 115. You know what the meaning of average? When you had all the 400 blood pressure for all the 400 people together, you now divide it equally and say, yes, we assume that all of you have the same. We have added all the blood pressure possible for the 400. We now divide by 400. We share it equally. We are saying that is not hypothesis is true that all of you have the same blood pressure. That's the meaning of. Because if you multiply the average by the number, it gives you the total thing you have together. So the mean, look at this first graph. You know, if you put your Y on the vertical axis, your S on the horizontal, the outcome measure you are looking at is the Y vertical. So let's say the mean value is the horizontal line. If the mean value of the horizontal line, look at the scatter. Look at the when you have already plotted the Y and X, you calculate the mean value of Y, you draw horizontal. Look at the distance of each value from the mean. Can you see? Look at the second graph at the top. You see second graph, that is the one that shows you the regression line. The example I gave now. You will see now, if I ask you, it's a lecture, you can talk. You can unmute at all. Which one is close? Which line is closest or closer to each point? Between the mean and the regression line, which one? I want people to make comment.
Regression line.
Thank you. Regression line. You see, the regression line is closer to those values than the mean line. It means that mean is a poor predictor. It's too far the mean is too far from most of those values. So it's a problem, it's the poor, and that is the simple one we shall get. It's the poorest. Now you now say, okay, yeah, it is obvious that the regression line is better. But you want to see, you want to evaluate the regression line. How much close? But there's no standard to use to compare. Apart from this mean, that is the evil you know is worse than it. Can you imagine? But how did the intelligent people do it? That they want to know how fit, how good this regression line is. And they are comparing it with one the regression line is better than, which is the mean. Now, this is the way they do it. You see, if you look at the distance, if you look at the total, because the mean is the crudest one. So the variability, if you look at it, is even if the average is farther from the line, and the line of mean is far from each value. If you calculate the variance there now, it gives you the total variance. You know, the variance is just you square the difference, all those different distances, and divide by the standard degree of freedom. It gives you the variance. So the total variability in this is what the mean has given you. Now, the model, if you look at the distance of each value from this model line, that is the error. That is the one, the error, what is in the data the model cannot account for. So you know that when we say we sum of square, you remember when we're doing our sum of square, when you say you are calculating variance, you say x minus x bar. X bar is mean. X minus x bar is the difference between x and x bar. We know that if you add them together, it gives you 0. Because some will be negative, some will be positive. Just like some will be above the line, some will be below the line. That's why they square it. When they square, they now sum it together. That's what we call sum of square. So sum of square, the sum of square residual, which is, you see, SSR, it uses the difference between the observed data and the regression line. So when you look at difference between the each data and the regression line, you square it. That is sum of square residual. And that is what is correct. That corresponds with the sum of square within that we did in the regression in ANOVA. You know, ANOVA, I told you there are 3 levels of variances. We say there's a variance between the difference between each group mean and the value of each group. The value in each group and each group mean, the distance, the difference is the variance within, sum of square within. We now say that sum of square between is the variance between each of the mean and the grand mean. Remember, it's the sum of square between. We now say sum of square total is the distance between each value and the grand mean. We now say that the sum of square total is the total variance in that data set, and the sum of square within and between add up to give you sum of square total. It's the same thing here. The sum of square total here is the difference between the mean and this first line and the and each value. Then the sum of square residual is the distance between each of these and regression line, which correspond with the sum of square within. This sum of square total here, this first one, corresponds with sum of square total in ANOVA. Then now let's now come to the last one. So if you overlap the two now, if you overlap these two graphs, that's what gives you the third one. We now see now we know that the total variance to be explained is what the first graph gave you. But the one this model cannot explain is the residual, this number 2. So the one the model can explain is when you remove the one it cannot explain for the total that is to be explained. When you overlap there, that the in between there, that difference, that is the improvement the model has made. That is the sum of square model. And this is one that corresponds with the sum of square between in ANOVA. So if you had sum of square residual and sum of square model, it gives you the total sum of square here. It's the same thing in ANOVA. So you can see that first graph, sum of square total using the difference between the observed data and the mean value of y. While the sum of square residual using the difference between observed data and the regression line. And the last, this one, sum of square model, M, using the difference between the mean value of y and the regression line. Now, the logic, if we now come back now, if you look, so this R square is sum of square model over sum of square total. Can you see now? Sum of square model, that is what the model can explain. The improvement, what we have gotten from the model, what it can explain. But the total to be explained is this sum of square total. So when you say you put what it can explain over what it can, the total to be explained, it gives you the percentage of what it has explained. That is variability in the y-axis, in y, the outcome variable, that is accounted for by the exposure. The exposure is the one that the model. So the variability out of the total variability of y that is to be explained, what proportion has been explained by the model? That is the R square. And whatever, if we have this thing, when we run it, when we do our workshop, you will see it, that you run regression, correlation between the two variables, you get your R. You will do your this thing like this one, this sum of square model divided by sum of square total. It will give you life. It will give you the same thing as if you square the correlation coefficient. That's what we call R square. They call it the coefficient of determination. This second one, if it also when the coefficient of determination is very high, having something 60-70%, you know that can you imagine this variable, this your model, that is the exposure variable, account for 70% of what is happening to outcome variable. Once something even account for more than 50%, that's the majority. It means that is the most important factor. Is the most important factor. Sometimes you do regression, you see we just account for 10%, even less than that. You now know that, well, if something account for only 10%, there are some other things that account for the 90%. But when something account for 70%, so other thing may account for 30%. It shows that that thing that account for 70% is the most important factor. So that is how we need to know relative contribution of the exposure to the outcome, coefficient of determination. Now, this F ratio is the same to look at sum of square model over sum of square residual. That is the ANOVA. If you remember, in our ANOVA, we say the sum of square between, that is variability between over variability within. And the variability between, what corresponds with it here is the sum of square model, this SSM. And variability within in ANOVA, what corresponds with it is the sum of square residual. So if we now divide this sum of square model over sum of square residual, it's like you are doing sum of square between in ANOVA over sum of square within. That is the regression. And that is the F statistic, which is the ANOVA. So I think we stop here. Maybe the next lecture, some of these other things are they are too technical. Yeah, so what maybe next lecture we'll still continue. Maybe I will bring, because I said I will demonstrate to you that ANOVA and regression is the same. That data on ANOVA, that's something on ANOVA. You want to use, we use it, maybe I'll prepare it and show you the same data. We'll run it with SPSS, it gives you the same answer. Maybe I will demonstrate that. Today is Tuesday, we'll do that on Thursday. I'm prepared to do that on Thursday so that it can share more light. So I don't know if there's any question. No question. If you are talking, you have to unmute. Oh. If you want us to hear you, you have to unmute. Prof, I thought you wanted to talk.
No. He's a slip of the finger.
Okay, sir. So, is it that it's confusing or it's easy? Dr. Enes, Dr. Wazo.
Okay. Okay. That's a draw. No, I got the illustrations. I think I got the principles.
Okay, that's it.
I think it remains for me to master the practical now.
Yes,
So
I think we have
maybe
run the
next session.
practical together before now. I think we have run the thing before.
Yes. Yeah. You know, this thing once you leave
If
it
you
leaves
don't
you.
do it constantly, yes, you
Yes. Yeah. I
it's
think.
very interesting. You know, ANOVA and
Uh,
regression, they are the same. It's a very interesting thing. Sometimes when you run them, begin to see the way these things are. You know, sometimes when you do regression, some of the I was a time,